So now we talk about vector line integrals. So here's a little picture to help us out. So to understand the vector line integral, first we're going to look at the graph, then we're going to talk about which quantity we actually hope to extract and calculate it, and then we describe how to do the calculation. So what's in this picture? We've got a vector field. So this is f equals x plus y, x minus y. That's the vector field. Okay, and that's in light gray. So now we've also got a curve. So the curve is just a basic unit circle. So the function is r equals cos t, comma sine t. Okay. Now, the only vectors we're interested in are the ones that are along the curve. So those are graphed in dark gray that you can see. So when we integrate the vector field along the curve, what we're saying is we're only looking at those integrals, only looking at those vectors. That's the first thing. Second, for a typical vector line integral, we're only going to extract the part of the vector which is tangent to, meaning in the same direction as, c. We'll talk about another possibility later. That's the one I want to focus on right now. So why would we want to only extract the part that's tangent to or in the same direction as c? So let's think of an application. What about when the physics application of work? So remember that force is a vector, so you think force is a vector field. Only the component of force in the direction of the movement is actually doing work. So that's why only that component it might be something of interest. So we can extract that value with a dot product, as we've seen before with work. So let's recall what we know about work. The basic case in which quantities are scalar and constant, work is just F times X. And as a reminder, W is work in joules, F is force in newtons, and X is just distance in meters. Now, in the case where quantities are scalar but varying, work is a function, and force is a function, and then the work is the integral from a to b of F dx. Next, where quantities are vectors but constant, work is force vector dot your displacement vector. So now we're going to consider the final case. So in the final case, what about where quantities are vector and varying? So by putting those two formulas together, the varying one plus the vector one, kind of smush them together, and what do we get? We get the integral, work being the integral of F, but now F is a vector, dot dx, but now that's a vector also. And we want to go from the start point to the end point. So we could write it this way. However, we don't usually write, or the notation that we have chosen to use is not writing the x as a vector x. That's the position vector, and we usually call that r. There are some notations where it is called the x vector, where we've been using r. So for our purposes, the way we're going to write this is that it's the integral of vector field f dot dr, where r is your position vector. So one way to see it is just kind of look at the formulas for work and just kind of smush them together. Another way to think it is the standard way that we construct an integral, which is think of the approximation. So a short piece of path, including the point Ri, is approximated by saying we've got a first point, say R3, and then a second point, say R4. And then you take, and how do you make that into a vector? You take R4 minus R3. And that's like a little piece, and that's a delta R. And then the value of the force, or the value of the vector on that segment, is approximately F of your point, which was Ri. And so the work done on that little piece of path is approximately your force there, F of Ri, dot your little displacement vector, which was delta R. That's the work on that segment. To get the total work, approximately add them all up. It's the sum of the force at that point dot your little displacement vector. But of course, we want to make this exact, so sums become integrals and deltas become d's. And that's another way to think about it. So this gives us our basic vector line integral formula. And we already know that we can use it to calculate work. Now, what it doesn't tell us is how do we actually calculate it. So just as before, to actually calculate it, we're going to have to write down everything parametrically. So let's do that. So R describes a curve. So R is really in 3 dimensions. So vector, so over here, vector R is really x comma y comma z, but parametrically everything's really a function of t. So it's x of t, y of t, z of t. And then for the boundaries, let's just assume that we're at the beginning point at t1 and the end of the curve, the piece of the curve at t2. Next, what about the vector function? So the vector function, we're again in 3 dimensions. The vector field f is really f of x, y, z, but again, each of those are functions of t. So next, we have to deal with dr. So what is dr? So these are all equivalent notations for dr. Let's take a moment to absorb this. So one way to think of dr is that it's r prime of t dt. But we also know that r prime can be written with the, we can write out the components. So it'll be x prime of t, y prime of t, z prime of t, and then of course all of that dt. That's one way to think about it. Another way to think about it is not using prime notation, using d notation. So dr, r is x, y, z, so dr is just dx, dy, dz. Now, of course, we know how to translate each of these individually. Dx is just dx dt times dt. Same thing, dy becomes dy dt times dt, and then dz becomes dz dt times dt. But now, dt is something that we can just factor out. But once we factor it out, we've got dx dt, dy dt, dz dt, and all of that can once again be written as just dr dt. So again, all of these are equivalent notations for dr. Use whichever you like. So put it all together and we get, I'll put down these 2 different parametrically written notations for the vector line integral. So the vector line integral, the general formula is the integral over the curve of vector f dot dr. And then we can write this out parametrically, either using d's or using primes. So f dot dr dt times dt, or the integral of vector field f, where it's a function of x of t, y of t, z of t, dot the vector x prime of t, y prime of t, z prime of t, and again, all of that dt. So again, however you want to write it down. Okay. So just one little comment. Remember that where does dr come from? Dr came from delta r. Delta r was a short vector between 2 nearby points. So it's sort of an approximation of a tangent vector. So dr, when we make it infinitesimal, is going to be, again, going to be a tangent vector. It's in the same direction as dr dt, which we already know is a tangent vector. So those are some comments. Now let's really get into it by doing a problem. So we've got a force vector field, f equals x plus y, comma x minus 2z, comma 2x minus y. And then over the straight line C defined by, and then there's the equation for it. And let's find the work. So in order to write down our vector line integral, we're going to need our parameterizations. So the parameterization for C already given. So now we can write down the parameterization for vector field F. Oh, sorry, and we should also, and then we'll also need the parameterization for dr. So dr, we know is just dr dt, dx dt, dy dt, dz dt times dt. So dx dt is just 3, dy dt is just -4, and then dz dt is just 4. And then all of that dt. And then also the parameterization for the function, plugging it in, x plus y becomes 1 plus 3t plus 3 minus 4t. Same for the y component, same for the z component. Bunch of algebra. Let's simplify it. Altogether, that gives 4 minus t, 5 minus 5t, -1 plus 10t. Put it all together, and what do we get? So the integral becomes So remember that it's always just the integral. So here we're finding work. So remember, it's always the integral over the curve of f dot dr. But we want to write that out parametrically. So it's the integral from t1 to t2 of vector field, but written in terms of t, times dr dt, all that dt. So we know our bounds were given. T goes from 0 to 1. We have our f written parametrically, and then dot dr, which we calculated 3, -4, 4 dt. And now you just have to do this integral. First thing in order to do the integral is take the dot product. So taking the dot product, you get 12 minus 3t minus 20 plus 20t minus 4 plus 40t, all that dt. Simplify, of course, and you just get minus 12 plus 57t. Integrate that dt. And once it's all worked out, it's actually a very simple integral. The tough part is always the setup. So this is just -12t plus 57 over 2t squared. Plugging in from 0 to 1, you get 16.5. And we were calculating work, so it is joules. Okay. So another problem, but in this case, there's one extra step. So find the line integral of vector field f equals xy, 2 minus yz, comma xz, over the curve C, which is the straight line from 2, 1, 2 to 5, 2, -3. So, what is the first thing that we need to do? First thing is we know that we're going to need the parameterizations. So first rewrite parametrically. So C is a straight line going from A to B. How do we write the equation for that parametrically? So we know that to write the equation of a line in general, we need two things. We need a point and we need a direction vector. Well, we've already got a point. In fact, we've got two of them, but we need a direction vector. In order to make the direction vector, when you're going from point A to point B, the direction vector is just B minus A. So the direction vector is just 5, 2, -3 minus 2, 1, 2. That's just 3, 1, -5. So now our starting point is 2, 1, 2, so we'll use that for our point. The direction vector is 3, 1, -5. So the parametric equation for our curve, which is a straight line, is just r equals 2, 1, 2 plus t times 3, 1, -5. And of course, we're going to want that as a single vector, so we just put it all together. 2 plus 3t, 1 plus t, 2 minus 5t. Now, what are the bounds for t? Well, notice that t equals 0. Whoops. T equals 0 gets rid of that, and then we're just at our first point. And then t equals 1 is just going to add this, which is going to get us to our second point. So we want the boundaries for t to be from 0 to 1. And for these sorts of parameterizations of line segments, it always works out like that. So now we've got our parameterization of the curve, and that actually puts us exactly where we were in the previous problem. in terms of steps. So now we've got our parameterizations. Now we just write down our vector line integral. Oh, sorry, we also need dr. Forgot about that. So if this is r, then dr is just going to be the derivative times dt. So it's going to be 3, comma 1, comma -5, all of that dt. Okay, so now we've got everything written parametrically, and now we just plug it in. Oops, so I forgot again. We got to write down our function parametrically. Keep forgetting things. Okay, so just plug all that in. So x times y is really 2 plus 3t times 1 plus t. Next, 2 minus yz is really 2 minus 1 plus t times 2 minus 5t. Similarly for z, and then of course we want to simplify that using algebra. So then the function written the vector function written parametrically is just 2 plus 5t plus t squared, comma 3t plus 5t squared, comma 4 minus 4t minus 15t squared. And now, let's see, yes, now we have our curve written parametrically and our vector function written parametrically and dr written parametrically. And now we can do our vector line. Okay, so vector line integral is the integral over the curve of f dot dr. And now just plug it in. So the curve has boundaries t goes from 0 to 1. Vector field f is just this, which we just said. And then dr was 3, comma 1, comma -5 dt. Okay. So to calculate this, the first thing we're going to have to do is we'll have to take the dot product. So take the dot product and then simplify. Okay, there's just a whole bunch of algebra there, but after you take the dot product and simplify, you get -14 plus 38t plus 83t squared. Integrate that dt and then evaluate from 0 to 1. That part is pretty straightforward. So there's the integral, evaluate from 0 to 1. You get 32.67, or really 32 2/3. Okay. So that is how you do a vector line integral. And I want to point out that, of course, we can also have applications. What can the vector field represent? Well, we previously talked about it possibly representing a force field, and then the vector line integral gives you work. We can also calculate something called flow. So find the flow of water along a path C by calculating the vector line integral, where your fluid velocity field is this. So sometimes for a velocity field, we'll use vector v. We've done that before. So if your velocity field is 2x minus 3y, comma x plus y, and then your curve C is given by r equals t plus 3, 2t squared minus 4, t goes from 0 to 2. So your flow gives you basically how much fluid is moving along your path. So the flow is the vector line integral, and we just need to write it out now. So the integral over the curve of f dot dr. On the curve, we're given the boundaries for t are 0 to 2. The function is 2x minus 3, vector field is 2x minus 3y, but we're given the parameterizations. That's just 2 times t plus 3 minus 3 times y, which is 2t squared minus 4, comma, finish up your parameterization for the vector field, dot dr. So what is dr? Dr is just x prime, comma, y prime. So looking at your r, x prime is just 1, and then y prime is just 4t. And then all of that, dt. And there is your vector line integral set up parametrically. And now you just can calculate it. First, take the dot product, which gives you a whole bunch of terms, which you then need to combine and simplify. So you get 8t cubed minus 2t squared minus 2t plus 18. Integrate that dt. And that just gives you 2t to the fourth minus 2/3 t cubed minus t squared plus 18t. And evaluate it as t goes from 0 to 2. Plug it in, and you get 58 2/3. And then that's a flow integral. So there's different applications depending upon what your vector field actually represents.